So at the end of the last little bit, we were talking about this brick skyscraper, the Montauk, first 10-story skyscraper in Chicago. And I'd mentioned that its foundations were equally interesting as its exterior walls, right? The story of the brick structure versus the need for window space was matched by what it took to support a building this heavy on the soil in Chicago. The reason this is important in Chicago, maybe more so than other cities, is that Chicago has probably some of the worst soil to put a heavy building on. It is by a lake, it is at the mouth of a slow-moving river, and over the last 100,000 years or so, that river has just gently deposited silt onto the Indiana limestone that's down about 80 or 85 feet beneath the street level of the city. So that silt has all formed this very spongy clay, and the compressibility of the clay means that when you put a building onto it, it sinks, in the words of the New York Times, like a jelly cake. So what builders had to do in the 19th century was to spread the load of their skyscrapers out. And there is this one layer that's right about at the lake level, right about at water table, that's called hardpan, which is a sort of dried out or desiccated layer of clay that has significantly greater bearing capacity than the more liquid clay below it. Still not great, about 3,000 pounds per square foot. And as you can see here, what architects and builders did was to basically spread the load out with using stone pyramids. And the reason they use pyramids instead of continuous or linear footings was that they had to very carefully calculate each load, divide it by the bearing capacity of the hardpan, and come up with a sort of calculable stress, right? In other words, they needed to be very careful about being able to measure the weight of the building that they were putting onto the soil. If you do this with linear foundations, you're never quite sure how the loads are being spread through that footing. With isolated or pier foundations that are pyramids instead of walls, you can pretty clearly establish how much load is coming down on a column, therefore how much load is coming down on a pier, and you can size the pyramid so that its base spreads that load out over an adequate amount of hardpan. Now, in the case of the Montauk, they needed space in the basement for boilers. In 1885, electricity is just coming on as a legitimate technology, so every building needs space also for a generator or a dynamo. And these pyramid foundations got to be inconvenient. They took up a lot of space in the basement, just the same way that masonry piers took up a lot of space in the elevations of these buildings. Chicago is full of railroad engineering, railroad manufacturers. They're rolling a lot of iron rail at this point. And so what builders realize is that you can use some of that surplus rail that's maybe not good enough to put out in the countryside for trains, but that is still plenty strong and adequate. And you can make what are called grillage foundations. In other words, little like floating pads almost of steel embedded in concrete that can more efficiently spread the load out without taking up all the space that the pyramids take up. The bending capacity of iron and later the bending capacity of steel make this possible and basically give you back a room for the basement. Why is this important? Why bother thinking about the foundations if what we're interested in is the architecture above? Well, there's a sort of mindset that goes along with what are called isolated piers. If you think about traditional linear foundations, walls that come all the way down and sit on bedrock that's maybe just below surface as you get in parts of Manhattan and Boston. What you would think of then if you're taking those foundations up into the building is you would think of the building structure as basically based on walls, right? Continuing that linear structure up and maybe punching through it where you need windows, and then typically spanning between these bearing walls with iron girders or beams. If, on the other hand, you have these isolated foundations where you're trying to really take the load of a single column down and not confuse it with loads from other columns, right? Really think through just exactly what one column is bringing down and putting it onto a discrete portion of subsoil. Well, then you might start thinking of your building structure not in terms of walls, but in terms of piers. And that might make you think about a more skeletal approach to the building framing above. When you do this, you're no longer really thinking about punching windows through a wall. You're more thinking about filling in the space between the structure. And you can do this with brick, but you can also do this with glass. And so you can fine-tune the amount of elevation available to you for daylighting a little bit more freely. All the more so if you're putting these not on pyramids, masonry pyramids, but if you're putting them on iron grills or grillages. And you can imagine the foundation sort of inspiring what comes to be the sort of Chicago style above ground. This is maybe most notable in some of the work of Adler and Sullivan, where you can see that in this facade, for instance, they've really distilled the elevation down into a series of brick piers. Each one of those piers is going to sit on either a pyramid or a grill, but the conception of the structure from underground really becomes something about a more skeletal frame than something that's based more on structural walls. And that sort of gives Chicago its unique character. Builders and architects in Chicago take the skeleton frame more seriously as a kind of conceptual basis than those in New York or Philadelphia or Boston. And nowhere is this more evident than in this building by William LeBaron Jenney. This is 1879, so it's a cast iron and wrought iron structure. And you can see, if you look closely in the plan, that Jenney has basically backed up the exterior cast iron columns with a brick pier on the outside. Because the column and the pier are sharing the load, the pier can be smaller. Because these are all sitting on pyramid foundations, isolated pyramid foundations, Jenney's very naturally thinking of the building structure above as linear elements emerging from that, piers instead of walls. And he's filling in the elevational surface of the building with these very, very large windows, right? This building was criticized because workers felt like they were going to fall out of the building, right? The windows came down so low, bringing in an enormous amount of daylight. Now, you'll see, though, that there is plenty of brick in this building. Not only are the brick piers on the street fronts there, but there's a giant party wall, and there's a fairly thick wall on the elevation on the top of the plan. And some of that is there for fire reasons. The party wall is there to prevent fire from going from one building to the next. But some of it is there also to stiffen the building. Remember, one of the problems with cast iron is that it's brittle. You can't drill it. It's not ductile. You can't drill it or cut it or rivet it. And so you have to piece cast and wrought iron together with very kind of loose connections, because cast iron is not only hard to work with, but it's imprecise. The iron that comes out of the mold twists and shrinks in ways that are sort of unpredictable. And the place I think you can see this most clearly is maybe Jenney's most famous building, a structure that's often called the quote-unquote first skyscraper. This is the Home Insurance Building, which was built in 1884, demolished in the 1930s. And if you look at the plan, this has the appearance maybe of a more skeletal frame. Certainly the elevations of the building show that Jenney is thinking of the building as a skeleton, right? It's emerging from point supports down underground. But there's a lot of brick in this building. Not only the party walls, which you can see top and bottom, those are thick enough not only to prevent fire from getting from one building to the next, they are also thick enough to support the building. They're part of the gravity system, and they are part of the stability system. They keep the building upright in a windstorm. When you get into the sort of anatomy of the building, though, what you find is that the Home Insurance was built not only of an iron frame, which it's most famous for, sometimes called the first skeleton frame, but that iron frame is embedded in brick. And so this sort of cutaway shows the cast iron columns in blue and the wrought iron girders in green. The connections between those are necessarily loose. There's no good way to connect to cast iron in a method that's precise or that's tight. And so the brick jacket around all of that iron is there partly to make the frame stiff, right, to carry the lateral or wind forces that the building's going to experience. And for a few years, this is the common way to deal with not only some of the gravity load, but also the wind load that these buildings are experiencing. Hybrids where a loose iron frame is supported against wind by a thicker or stiffer brick jacket. Right across the street from the home insurance, this is Burnham and Root's Rookery building that is still there. This has a cast iron structure on the inside, and the exterior walls are all of brick. And you can see that they read as piers sitting on grillage foundations, same as the Montauk. But in this case, the brick piers on the outside are literally just brick. There's no iron reinforcement as there is at the lighter store. There's no embedded iron as there is in the home insurance. These are pure brick piers, and they are not only holding the exterior of the building up, but they are providing the building's lateral stability. This is the age-old problem, same problem as the Montauk. The windows and the structure are fighting for space on the elevation. And a few years later, a firm called Halliburton Roche solved the problem by taking all of those brick shear walls, basically, that are on the outside of the building and turning them 90 degrees. So they're perpendicular to the elevations and they run through the inside of the building instead. You can see in the Tacoma that this opens up a huge amount of space for windows on the outside. But you can see also on the interior that those shear walls still take up space. They're not preventing the building from being illuminated by sunlight anymore, but they are restricting what the planning of the building can do, right? They're giant 18 or 24-inch shear walls in the way that are hard, if not impossible, to sort of excavate through. So the buildings of the late 1880s, early 1890s are hybrids, and they're hybrids in other ways as well. They use terracotta not only for or terracotta and brick not only for the exterior, but also for fireproofing, a way to prevent the sort of failures that happened in the 1871 fire. So steel or iron columns, steel or iron girders are protected by this thin jacket of terracotta fireproofing. And floors, as you can see, are composed of this hollow terracotta tile that's designed to be a flat arch. You might remember talking about flat arches in Roman times. Well, here it is in a slightly different material. On the right, you see other developments in fireproofing that include not only the kind of flat arches, but also the bottom two are early efforts at concrete floors. Concrete floors, of course, are what we use standard today to create fireproof barriers between one level and the next. As we'll see in a couple of lectures, concrete is still a relatively newly rediscovered technology in the 1890s. It's not quite to be trusted. It takes a few years for it to replace terracotta. Here you can see the Tacoma. This is an elevation on the left, so this is a lot more glass on the elevation, a lot more daylight coming in. The Tribune complains that this is a building that looks so fragile that people are worried it's going to fall down into the street, and it has to explain to people that the wind bracing, the walls that keep it from being blown over in a windstorm, are just hidden, right? They're on the inside. And again, here you can see the light green is cast iron, the dark green is wrought iron. So the same problem with stiffness, but now that's taken up by these giant shear walls. And then you can see the terracotta arches or fireproofing that runs in between the beams that's providing both a sturdy floor and a barrier to prevent fire from going from one level to the next. So clients would still like to get rid of these massive shear walls. They take up space, they affect the planning of the building, and the solution that comes along comes from the development of steel. And in particular, the Bessemer process, and in Chicago, a variant of that called open hearth, that basically allows fabricators to fine-tune the ingredients of the iron. You may remember seeing the Bessemer converter and the idea that the air that gets blown through the molten steel removes all of the carbon, and then you're able to come in and very precisely put carbon back until you get to this sort of magic level of carbon content that makes the steel both equally strong in compression and tension, but also very ductile and therefore reliable. More importantly, able to be worked, right? Cut, drilled, and riveted. And what this means in William LeBarry Jenney's terms is that they can take the methods that they've been using in wrought iron railroad bridges, and they can turn them on end. They can make buildings that are, as Jenny says, built like bridges. Instead of a truss spanning from riverbank to riverbank, though, what Jenny is talking about is taking that truss and making it into a cantilever that sticks up from the earth, basically, and that resists the wind loads in the same way that a truss bridge resists gravity loads, just turned at 90 degrees. And the secret to this lies in the details. If you look at the connection details for cast iron columns, as I said, they have to be very loose. The iron that comes out of the mold has cooled and it's shrunk in ways that you can predict but not be entirely sure of, and very often it's twisted. So if you put a hole into a cast iron column, there's no good way of guaranteeing exactly where it ends up. If, on the other hand, you want to put a hole into a steel column, you simply roll the steel, and then you come back, and because it's ductile, you can drill into the steel exactly where you need the hole to go. Because it's ductile and not brittle, you can also drive a hot rivet into the steel with hammers, and you can get a guaranteed very, very tight, very precise, very stiff connection between girders and columns. And what this means is that the steel frame can now take all of the lateral forces that the shear walls are resisting in these hybrid buildings, and it can actually resist those forces on its own, right, within the frame. And we'll see how this develops in a couple of different ways. There is a native steel industry in Chicago. It is at the junction basically between shipping routes that allow it to bring iron ore from northern Minnesota and railroads that bring coal from southern Illinois. And you can see that in the era of steel, when steel basically comes online in the late 1880s, the average height in Chicago skyscrapers jumps. And it jumps to the point where developers begin agitating for higher and higher height limits after about 1890. What do these look like? Here's one of the earliest wind-braced steel frames in Chicago, the Old Colony building, which used a technique borrowed not from bridges but from shipbuilding, the portal frame. And you can see here there's a giant steel plate carved around this or wrapping around this elliptical ceiling form. And that steel plate is making the firmest possible connection between the columns on the left and right and the floor girders on the top and bottom. The angle between the column and the girder is going to be 90 degrees no matter what. And when the wind tries to rack the building, what's going to happen is that every member of the steel frame is going to be recruited into resisting it. The angles can't change, so it won't make the rectangle into a parallelogram easily. What has to happen is that all of the columns and all of the floors have to actually bend. And in doing so, their resistance to deflection will end up resisting the wind. A year later, or about the same time, this is the Masonic Temple by Burnham and Root. This was the tallest building in Chicago. And depending on how you define it, maybe the world for a very short period of time. And you can see, looking at this section, that it is literally like a truss bridge turned on its end, anchored into the ground, but using trusses and riveted connections to give the building a lateral system, a way to resist wind loads in the short direction. Sometimes these were hybrids. This was the Pontiac building, where you can see that it has steel columns but uses these two masonry walls as its lateral system. And maybe most interesting is the Monadnock, which we always think of as a masonry building. And there is certainly a lot of brick in the Monadnock. It has the reputation as the tallest masonry skyscraper at 17 stories. And what you always hear is that this is proof of the kind of limits of masonry construction, because the brick, as you can see, swells as you get down to the ground floor, and it takes about walls of about 6 feet thick to carry the load of the masonry above. Right, most of the brick in the Monadnock is carrying other brick. Right, the brick is so heavy that you end up sort of chasing your tail, trying to carry all of it. If, though, you crack open the Monadnock and look inside, you see that it too is a hybrid, and it's using not only brick but also steel for its gravity load. You can see steel columns carrying the interior structural elements, But you can also see that there are portal frames, right? These trusses that go between the columns, those are doing some of the work of stiffening the building against wind. And so the monadnock, even though it's detailed on the outside to look like a masonry skyscraper, is really a hybrid. I think of it as a steel skyscraper, sort of modern steel frame on the inside, trying to get out of an old-fashioned masonry jacket. Masonry continues to show up on the exterior of Chicago buildings and buildings nationwide as well. And there's a little bit of a conundrum there, right? If you have the steel skeleton frame, why is it that buildings like the Masonic Temple, why is it that that building is still clad in mostly masonry? Why are the windows still small if the steel frame should allow much, much bigger openings? That is what we'll look at in the next piece of the lecture. We'll look at material technologies that change and offer new alternatives for the skins of buildings that in turn permit more glass and permit more daylight to come in through the skin, allowing architects to take fuller advantage of the possibilities inherent in the steel frame.